Let's solve problem 5.55 from Microelectronic Circuits 8th edition by Sedra and Smith. For each in the circuit shown, find the labeled node voltages, and for all transistors, Kn prime times W divided by L is 2 milliamps per volt squared, and the threshold voltage is 0.5 volts, and then the channel length modulation is 0. So, for any circuit analysis problem with a MOSFET, you need to answer two questions first. Is the device PMOS or NMOS? And then the second question is, what is the region of operation? So let's answer the first question first. It kind of already gave it away by saying Kn prime. But the way you can tell on a circuit schematic is if the arrow is pointing into the channel or out. So here it's pointing out. So that's how you know it's an NMOS. If it was a PMOS, there would be an arrow pointing into the channel like this. So because this is an NMOS, I can define this upper channel to be my drain, the middle one to be my gate, and the bottom channel to be my source. If this was a PMOS, then your drain and source channels would be flipped. Now the next question is, what is the region of operation? Well, I can see that my voltage at the drain is 0 because it's grounded. Likewise, the gate is grounded, so it has 0 voltage, which means my voltage from drain to gate is equal to 0. And we know that if the voltage from drain to gate is less than or equal to threshold voltage, then we are operating in saturation because threshold voltage is 0.5. So now we can leverage the drain current equation in saturation. I'm going to use it to solve for V overdrive and then use that to solve for V1. So let's do that. So the current equation in saturation is ID is equal to 1/2 times Kn times V overdrive squared. So we say V overdrive squared is equal to 2 times ID divided by Kn, all that under a square root. So V overdrive will be 2 times, I'm going to convert all the units to amps. So it is, see the drain current here is 10 microamps. So we're going to do 10 times 10 to the negative 6 amps divided by 2 times 10 to the negative 3 amps per volt squared. Plug that in and we get 0.1 volts. So now I can calculate my voltage drop across the gate and source, because that is the threshold voltage plus the overdrive. So that's 0.5 volts plus 0.1 volts, which is 0.6 volts. So V1 is really just the voltage at the source, neglecting this negative 2 volts here. So that's really just the voltage at the gate minus the voltage drop across the gate and source. Now we know the voltage at the gate is grounded at 0, so it's going to be 0 minus my voltage from gate to source, which I just calculated as 0.6 volts. So therefore V1 is equal to negative 0.6 volts. That takes care of the first circuit. Let's move on. Okay, let's solve circuit B. So again, it's an NMOS because the arrow is pointing outside of the gate channel. We can see drain is grounded at 0, gate is grounded at 0 volts. Here's our source, V2. We know that the voltage from drain to gate is equal to 0, which is less than the threshold. So this device is in saturation. So we can say ID is equal to 1/2 times Kn times V overdrive squared, and therefore V overdrive is equal to the square root of 2 times the drain current divided by Kn. So here our drain current is 100 microamps, which I'm going to convert to amps, so 100 times 10 to the negative 6 amps, divided by Kn, which is 2 times 10 to the negative 3 amps per volt squared. So I get that V overdrive is 0.316 volts, which means that the voltage from gate to source is equal to threshold voltage plus overdrive voltage. And so that is equal to 0.5 plus 0.316, which is equal to 0.816 volts. And using that information, I can solve for V2 because V2 is equal to the voltage at the gate, which is 0, minus the voltage drop across the gate and source. So that's equal to 0 minus 0.816, which means that V2 is equal to negative 0.816. And that solves the circuit. Okay, let's solve for circuit C. This is pretty similar to the last two. We have an NMOS device, and we have the drain grounded at 0 volts, gate grounded at 0 volts. And we know that the voltage from drain to gate is equal to 0, which is less than the threshold voltage. So once again, this device is operating in saturation. So our current equation is 1/2 Kn V overdrive squared. So V overdrive is equal to the square root of 2 times the drain current divided by Kn. This time the current is 1 milliamp, so it's going to be the square root of 2 times 1 times 10 to the negative 3 amps divided by 2 times 10 to the negative 3 amp per volt squared. So I get that V overdrive is equal to 1 volt. This means that the voltage from gate to source is equal to the threshold voltage plus the overdrive voltage, which is 1 volt, plus 0.5 volts. Sorry, I flipped the 2. So you get 1.5 volts. And V3 will be the voltage at the gate minus the voltage across the gate and source. So V3 is equal to 0 volts minus 1.5 volts, which is equal to negative 1.5 volts. So that is our answer for this problem. Let's continue. Okay, let's do circuit D. So again, we have an NMOS because the arrow is pointing out. Now, this time we have the current source at the drain wire. The drain we are reading is still right here at this node, V4, which we can see is equal to the voltage at the gate because it's shorted right here. You can tell by this wire that the voltage at the drain is equal to the voltage at the gate, which will also be equal to the voltage 4. So that means that the voltage drop from D to G is equal to 0 because they're equal to each other, which once again is less than threshold voltage. So this device is operating in saturation. So we can establish our drain current equation again of 1/2 Kn V overdrive squared, and I'm going to solve for V overdrive equal to the square root of 2 times the drain current divided by Kn. This time the drain current is 10 microamps, which I'm going to convert to amps. Convert Kn to amps per volt squared. So 2 times 10 to the negative 3 amps per volt squared. So I get that V overdrive is equal to 0.1 volts. And that means that VGS is equal to threshold voltage plus, wow, that is not a good plus sign. Okay, so it's the threshold voltage plus the overdrive voltage. We're going to make a good plus sign. Okay. Plus V overdrive. So that's equal to 0.5 volts plus 0.1 volts, which is 0.6 volts. And knowing this information, we can solve for V4 because V4 is simply the voltage at the source right, if we're traveling up from the circuit, it'd be the voltage at the source plus the voltage drop across the gate and source, because that'll take us to the voltage at the gate, which is equal to the voltage at V4. And we can see that the source is grounded, so it's just going to be 0 plus 0.6 volts. So V4 is equal to 0.6 volts. Okay, let's move on to the next circuit. Okay, let's solve circuit E. So again, it's an NMOS with our drain being red here at V5. Once again, the drain is being shorted to the gate, so these are all equivalent, and we have our source grounded at 0 volts. Okay, we see that the voltage from drain to gate is equal to 0 because they're equivalent, which is less than our threshold voltage. So once again, this is operating in saturation. So we have ID is equal to 1/2 Kn V overdrive squared. So V overdrive is equal to the square root of 2 times the drain current divided by Kn. Now this time the drain current is 1 milliamp. So 2 times 1 times 10 to the negative 3 amps divided by 2 times 10 to the negative 3 amps per volt squared. I get that V overdrive is equal to 1 volt, which means that the voltage from gate to source is equal to the threshold voltage plus our overdrive voltage, so that's 0.5 plus 1 is equal to 1.5 volts. And then we can calculate V5 being voltage at the source plus the drop across the gate to source. So that's equal to 0 plus 1.5 volts. So we get that V5 is equal to 1.5 volts. All right, let's move on to the next circuit. Okay, let's solve for circuit F. We still have an NMOS device, and we have our source equal to 0 volts. We have V6 equal to the drain voltage, which is shorted to the gate voltage. We know that voltage from drain to gate is still going to be 0, which is less than or equal to threshold voltage, so therefore we are in saturation. But this time we don't know the current. Looks like we just have a resistor and a voltage source. So I'm going to start with this equation. ID equals 1/2 Kn V overdrive squared. We can express current using nodal analysis as 2 minus V6 divided by 140 kiloohms. We can set that equal to 1/2 times Kn times V overdrive squared. So right now we have 2 variables and only 1 equation. So we need to probably express V6 and V overdrive into VG or VGS. Probably VGS. So on the right side we can express V overdrive as VGS minus VT squared. And on the right side, well, V6 is equal to VG. And we know that VG minus VS is equal to VGS. But VS is equal to 0. So therefore VG is equivalent to VGS in this problem. So we can do 2 minus VGS divided by 140 kiloohms. So let me just go ahead and plug in all of our values. So it's equal to 1/2 times 2 milliamps per volt squared times VGS minus 0.5 volts squared. Okay. So now we just have to solve for VGS. So I'm going to multiply this 140 kiloohm to the right side. And milliamp is 10 to the power of negative 3. And kiloohm is 10 to the power of 3. So these units will just simplify. So we'll have 2 minus VGS. And really that just means we have 2 divided by 2. So it's just going to be equal to 140 times VGS minus 0.5 volts squared. Okay, let's expand this. So we have 2 minus VGS equal to 140 times VGS squared minus 2 times VGS times 0.5, so just minus VGS. Plus 0.5 squared is 0.25. And we can distribute the 140, so we have 2 minus VGS is equal to 140 VGS squared minus 140 VGS plus 140. Quarter of 140 would be 35. Okay, and let's get everything to one side of the equation. So we'll have 140 VGS squared. We're going to add a VGS to get, what did I write in equals? We're going to add a VGS to the other side, so it's going to be minus 139 VGS now. Okay, fix that up. Minus 139 VGS. We're going to subtract 2 to the other side, so we're going to get 35 minus 2 to get plus 33 equals 0. And so it looks like we can just solve this with the quadratic equation, so I'm going to continue up here. So we're going to have VGS is equal to negative 139, so 139 plus and minus the square root of 139 squared minus 4 times 140 times 33, all divided by 2 times 140. Oh, this is disgusting. Okay, so I can tell you now that pretty much anytime we're doing a MOSFET device, you'll notice I've taken a lot of square roots already in this problem. It's always going to be the positive one, not the negative. So you're going to take the positive square root answer. And so it looks like we get 0.6 volts. So VGS is equal to V6, which is equal to 0.6 volts. That is our final answer. That was a lot harder than the previous ones. But let's keep going. Alright, so we have circuit G here. You can see it's very similar to the last circuit. So I'm going to just skip straight to solving for the value of VGS, which we know is same as V7, and this device is operating in saturation. So we can express the current as 2 volts minus VGS divided by 0.5 kilo ohms. And that'll be equal to 1/2 times Kn, which is 2 milliamps per volt squared, times V overdrive squared, or VGS minus the threshold voltage squared. I'm just going to actually plug in that value of threshold voltage right away. So once again, we're just going to be solving for VGS. Okay, so I'm going to multiply this 0.5 kilo ohms to the right side, which will cancel out the milliamp and kilo ohm units. So we basically have 2 times 0.5 is 1, so we just are left with this 1/2. So we have 2 minus VGS equals 1/2, and I'm going to expand this exponent. So we're going to get VGS squared minus VGS plus 0.25. Let's expand or distribute the 1/2. So we get 2 minus VGS is equal to 1/2 VGS squared minus 1/2 VGS, and then 1/2 of 0.25 is 0.125. And then let's get all the terms on one side. So we're going to have 1/2 VGS squared plus 0.5 VGS. And then we're subtracting 0.125 minus 2 is negative 1.875. We're going to use the quadratic equation. So VGS is equal to negative 0.5. Again, we're only concerned with the positive square root, adding it, of, okay, so 0.5 squared minus 4 times 1/2 times 1.875, all divided by 2 times 1/2. Okay? So I get that VGS is equal to 1.5 volts. And I'll explain why real quickly we only do the positive. So if I did the negative, I actually get negative 2.5 volts, which makes no sense given the structure of this. We have 2 volts here. And if I'm supposed to have a negative drop of 2.5, then I should get 4.5, right? So that just doesn't make sense. That's why we always do the addition. So V7 is equal to 1.5 volts. All right, I believe we have one more circuit, so let's take care of that one. Okay, we're here for circuit H, and you'll notice I brought back circuit A, and that's because I think I just realized something that also could have been applied to the last 2 circuits. But we'll notice that circuit H is very similar to circuit A, except this current source has been replaced by a 140 kilo ohm resistor. So I think because of that, we can just state that V8 is equal to the value we got for V1, which was negative 0.6 volts, and this does check out because if we try to calculate the current using these parameters, if I want to calculate drain current across here, that would be negative 0.6 volts minus a negative 2 volts, so plus 2 volts, divided by 140 kilo ohms, and sure enough, that's 10 microamps. So we probably could have done this for the last 2 circuits too. I don't know if this was the author's intention, but I also don't feel like doing another quadratic equation. So I'm going to go with that. Thank you for watching this video. If you have any questions or video suggestions, feel free to contact me in the comments or by my email. And I hope you'll have a great day.